Welcome everybody. Let's look at more into real number systems. Okay, so let's look at the proof. The proof is as follows. So what we do is, so let A be the set of all the left endpoints, set of all left endpoints of Jn. Okay. So what I am considering is that is AB set of all An, right? N in N, right? So I'm considering all the ANs, right, where N belongs to N, right? So A1, A2, A3, and so on, right? Uh, so since JNs are closed intervals, right, this would imply that A is always non-empty, right? Isn't it? All right, let's change the pen. Boom. Okay, so my claim is, what I'm claiming is that A is bounded about by bk for every k in N. That is what I want to show is ANs are less than or equal to bk for every n in N and for every k in N. This is what I want to try. This is what I want to prove. Let's understand the situation first of all. What we have rather is, let's look at that with the help of a figure. What's given to us is whenever a number is bigger than the other, like if n is bigger than m, then the interval with endpoints a, m, b, n would be contained inside an. So in this case, what will happen is the outer interval here would be a n, b, n, and it will contain a, m, b, n, right? That's what we have, right? So this is what I have to show that this is true. Okay, so let's try to prove. So this is true for any n in n, any k in any k in n, right? So let's take case one. Case one is if my n is bigger than or equal to k, right? What if n is bigger than or equal to k, right? This would imply that jk would be contained inside jn, right? Sorry, it's opposite other way. If n is bigger than k, then what will happen is, yes, jn would be contained inside jk, right? Jn would be inside jk, isn't it? This would imply that what is jn? Jn would be an comma bn, right? Would be contained inside ak bk, right? So let's kind of understand this with the help of a figure. Always keep a figure in front of your eyes. Okay, so what we have here is we have ak here, bk here, and then we have an and bn inside that. So from here what we get is, therefore what happens is ak would be less than or equal to an, that would be less than or equal to bn, that would be less than or equal to bk, right? So from here, let me name this as 1. So from here it is clear that all the ANs are bounded by this bk's. Okay, case 2. Let's look at what's the case 2. If n is less than k, right? This would imply if n is less than k, then jk would be contained inside jn. This would imply that ak bk would be contained inside an bn, right? Again, let's draw the figure. This is closed interval, by the way. Let's draw the figure and understand this properly, right? What do you mean by this? Let's look at here, right? Change some different pen so that we can make it. Okay, so what we have is the outer interval now would be an, and this is Bn, and the inner interval would be AK and the yes, right? So even if I write the same thing here, what I get is An less than or equal to AK, less than or equal to BK, less than or equal to Bn. Let me name this as 2. Therefore, from 1 and 2 we get ANs, right? If I look at 1 or 2, what happens is ANs are always less than or equal to BK for every n in n, for every k in n, right? Hence, what we get is A is bounded above by pk for every k in n, right? Bounded above by every k in n. Therefore, what we get is therefore A is a non-empty subset of R, which is bounded above, right? Bounded above. Therefore, by order completeness of R, right? What we get is A admits a supremum in R, say C. That is, C is equal to supremum of A, right? So what happens is we get A to be the supremum of C. So let me name this as claim 1. So I have already fulfilled claim 1 here. Let's make a claim 2. Okay. Claim 2. Whatever the supremum is, this belongs to Jn for every n in n. Okay. So note that C is the supremum of A, right? This would imply that ANs are all less than or equal to C for every n in n. Also, note that Bn's are upper bound of A, right? For every n in n. Therefore, what should happen is, since Bn's are upper bounds of A, therefore what should happen is and C is the least upper bound. C is the least upper bound of A. Therefore, C must be less than or equal to Bn for every n in n, right? Therefore, if I combine this, right, let me name this as 3 here, let me name this as 4 here. Therefore, from 3 and 4, we get is An is less than or equal to C, less than or equal to Bn for every n in n. That is, C belongs to An, Bn for every n in n, right? Therefore, C belongs to Jn for every n in n. That is, therefore, intersection n in n has of Jn has C in this. This would imply that intersection n in n of Jn is non-empty, and that's the point set game for this theorem. All right, let's look at something else. So this is the theorem which is called as nested interval theorem. Okay, let's look at more of properties of real numbers. Okay, so let's look at this function called as absolute value function or modulus function. You must have seen these things. So what we have is absolute value function, or it also called as modulus function. whatever you want to call it. Okay. All right. So let's define this. Let f from R to R plus union 0, right, be such that f of x equal to x whenever it's a positive number, and it's equal to negative of x whenever it's a negative number, right? Then f of x is called as absolute value function, right? And absolute value function and is denoted by modulus of x, right? That is, modulus of x is nothing but x whenever x is positive, and it's negative of x whenever x is negative. Okay. So if I look at the graph of this function, let's look at the graph of this function quickly. So yeah, so if I look at the graph, as I said, so I'll draw it here. Okay. So if I look at the definition of the function, it's positive, right? Whenever, okay, let's take a line. So if I look at the definition of this function, it's positive whenever x is positive. So it's at 0, it is 0, of course. Okay. And whenever it's positive, it's identity function, right? So it goes to, the line would be like this, something like this, right, on the positive half side. And whenever it is negative of that number, right? So what would happen is, whenever I have this way, right, it would be this way, right? Let's call that properly, something like this, right? So this would be my graph, right? My graph is not proper, but I hope you can make a sense out of it, right? So it's exactly like a V, right? So this is a graph. This is my x-axis, y-axis, right? So what happens is, whenever x is negative, its value is positive. Whenever it's positive also, its values are positive, right? So that's a graph of the function. Okay. Let's quickly take up a remark, and then we'll see the properties of modulus functions. Remark: note that modulus of x is same as maximum of x comma negative x. Okay. So recall, maximum of any two numbers is the biggest number between a and b, so it will be bigger than or equal to a, and at the same time maximum of a comma b would be bigger than or equal to b. So you need to recall this. Therefore, if x is bigger than 0, right, what will happen to maximum of x and negative x? If x is a positive or equal to 0, then what will happen is, this would be always x. By definition of modulus function, this is modulus of x. Whenever x is 0, modulus of x is x, right? Similarly, if x is negative, right, maximum of x and negative x, if x is negative, this implies minus x would be positive. So the bigger number between x and negative x would be negative x. This is by definition whenever x is 0. Minus x is the definition of modulus x, right? Therefore, what I get is maximum of x comma minus x is always nothing but modulus of x, right? So let's look at the properties of the modulus function. So let's look at case 4. Case 4 is on the similar lines as case 3. What if x is positive and y is negative? Here this would imply that again xy is negative. Since x is positive, mod x is x, y is negative, mod y would be minus y, and this is true. This would imply that, this would imply that, this would imply that mod xy would be negative of xy. Therefore, if I use this xy, which is nothing but negative of x dot y, which is nothing but x into negative of y, which is nothing but x is nothing but mod x, negative y is nothing but mod y. So here also I get the same result, right? And then let's look at the final case, case 5. If x is also negative, y is also negative, this would imply that xy would be positive. Since so this implies that xy would be nothing but, right, isn't it? So since x is negative, modulus of x is negative x, y is negative, modulus of y would be also negative y, right? Therefore xy, which is would be nothing but so what will happen is, okay, I can do it in the reverse way. Therefore modulus of x into modulus of y would be nothing but minus x into minus y, but these are two real numbers. Negative becomes positive, and what you get is x y, but this is nothing but mod x into mod y, right? Therefore what we get is mod x y is nothing but, all from all 5 cases, what you get is mod x is nothing but this for every x comma y in. That's the first property done. Let's look at the second property, a different color, 2. Okay, or can use general 2 also, no problem. Second one, these are small ones, easy. Mod x square is nothing but x square for every x in R, right? Proof, note that let's look at the cases here also, but okay, so note that if x is bigger than or equal to 0, mod x is same as x, right? Therefore uh, mod x into mod x, which is nothing but mod x square, this would be equal to x into x, right, which is nothing but x square. Therefore, okay, I should have written this side, but anyway, okay, doesn't really matter. Okay, mod x square is nothing but mod x into mod x, which is x into x, which is x square. Similarly, if x is less than 0, this would imply that mod x would be equal to negative x. Therefore, mod x square would be nothing but mod x into mod x again, but this is negative of x, this is also negative of x, negative of negative would be, this would be nothing but negative x squared, which is x squared, right? So that's, therefore what we get is mod x square is x square for every x in R, right? That takes care of the second property, right? Let's look at the third one. So property number 3, okay, what we have is modulus of x is always bigger than or equal to positive x, and modulus of x is always bigger than negative x. That is, modulus of x is always bigger than or equal to plus or minus x. Oh, this is pretty simple. Uh, we know that modulus of x is equal to maximum of x negative x, and maximum of x comma negative x is always bigger than x and both of its numbers, right? Recall this, maximum of a comma b, as I said, will be bigger than a, and maximum of a comma b is always bigger than b, right? So this x comma minus x will be always bigger than negative of x. Therefore mod x becomes, therefore x is, if I combine both, is bigger than plus or minus x. Let's look at the fourth one quickly. So these are some small properties, we can just deal with them right away. Okay. Then fourth one says that, let me use some different pen for this. Negative of mod x, this is true for every x, right? This is true for every x in R. Okay. Mod x is less than or equal to x, less than or equal to mod x. Proof. Okay, note that mod x is bigger than or equal to plus or minus x from this theorem, right? That is, mod x is bigger than or equal to minus x, right? Therefore, what we get is mod x is bigger than or equal to x, and if I multiply both sides by negative sign, what happens is x becomes less than or equal to, if I multiply by minus sign, inequality will reverse, right? So yeah, what we get is x in this case would be bigger than or equal to negative of mod x. That is, minus mod x from here is less than or equal to x, and x is less than or equal to mod x. So this is like a less than b and b less than c. Therefore, minus x would be less than or equal to x. That would be less than or equal to mod x. And this is true for every x in R. This is true for every x in R. For every x in R, just mention this. Every x in R, right? For our convenience. So that comes with the fourth property of modulus. Let's look at the fifth one. Okay, what's the fifth property says? It says that x modulus of a real number is less than epsilon, right? If and only if x belongs to minus epsilon, the interval x belongs to the interval minus epsilon comma epsilon. Let's prove this. Proof pretty much easy. Suppose modulus of x is less. So this is, suppose modulus of x is less than epsilon. This implies that maximum of x and negative of x would be less than epsilon. This implies that x would be less than epsilon and negative x also would be less than epsilon. This means that x is less than epsilon and multiply by negative sign, what I get is minus epsilon, right? Would be, if I multiply by minus sign, the inequality would reverse, right? And what I get is minus epsilon in this case would be less than x. Therefore, what I get is minus epsilon is less than epsilon, right? So if I combine this, this would imply that x is between minus epsilon and epsilon. Therefore, x must be inside the interval minus epsilon, right? Conversely, let's look at the converse. Conversely, suppose x belongs to minus epsilon epsilon. I have to show that the modulus is less than epsilon. So just go opposite. So this would imply that negative epsilon is less than x, less than epsilon. This would imply that negative epsilon is less than x and x is less than epsilon. This would imply that minus x would be less than epsilon and x is also less than epsilon. This would imply that maximum of minus x and x would be less than epsilon. This would imply that mod of x is less than epsilon, because this is equal to mod x, right? That's what we have proved in the beginning. So this finishes the property number 5. Let's look at the property number 6. So all in the similar lines. Okay, property number 6 says that x minus a is less than epsilon if and only if x belongs to a minus epsilon, a plus epsilon. Just putting a here, right? So let's prove this. Doesn't really matter. Okay, so what would happen is, if this is true, then if mod of, suppose mod of x minus a is less than epsilon, this would mean this just mechanical. X minus a, negative of x minus a is less than epsilon. this would mean that x minus a is less than epsilon and negative of x minus a is less than epsilon. This means that x minus a is less than epsilon and multiply by negative sign minus epsilon, inequality will change, right? Minus epsilon would be less than x minus a, right? If negative of this, then what will happen is this would be bigger than minus of epsilon. That's what we have. Add a on both sides, what I get is this would imply that x would be less than a plus epsilon and minus a minus epsilon. If I add on a on both sides, minus a minus epsilon would be less than x. Therefore, a minus epsilon would be less than x and that would be less than a plus epsilon. This would mean that x belongs to, this would mean that x belongs to a minus epsilon, a plus epsilon. Conversely, how do we do converse? Conversely, suppose x belongs to a minus epsilon, a plus epsilon. This means that a minus epsilon would be less than x less than a plus epsilon. This would mean that if I add a minus epsilon would be less than x minus a, right? Less than epsilon. This means that minus epsilon is less than x minus a and x minus a is less. X minus a is negative of x minus a is less than epsilon and x minus a is also less than epsilon. This means that maximum of x minus a, negative of x minus a, both are less than epsilon, right? Just the way we have done the previous one. This means that modulus of x minus a, because this is nothing but modulus of x minus a, that would be less than epsilon. Hence the proof, right? So as I said, it's just too mechanical. You got to just go about the proof. It's too mechanical. These proofs are just follows from one another. Let's look at the seventh property. This is called as x plus y is always less than modulus of x, modulus of y, for every x comma y in R. This is called as triangle inequality. Triangle inequality. All right. How do we prove it? Let's look at this one. So proof pretty much simple. Yet a bit of work is required, but anyway, we would do that. Note that x plus y squared is nothing but x plus y squared. This would be x squared plus 2xy plus y squared if I use a binomial theorem. But x squared is nothing but modulus of x squared plus 2 times xy plus modulus of y is same as modulus of y squared, right? Note that if I observe, modulus of x is always bigger than or equal to x, right? And modulus of y is also bigger than y for every x comma y in R. Therefore, x into y, if I multiply this x into y, right, would be less than or equal to, because x is less than modulus of x, y is less than modulus of y, so xy would be always less than or equal to modulus of x into modulus of y. Therefore, 2 times xy would be less than or equal to 2 times mod x mod y, right? Isn't it? So we just put it here. Therefore, x plus y the whole square is equal to, which was equal to modulus of x square plus 2 times xy plus modulus of y square, now would be less than or equal to modulus of x square plus this is less than 2 times mod x into mod y square. So this is equal to modulus of x plus modulus of y the whole square. Therefore, modulus of x plus y the whole is less than or equal to modulus of x plus mod y. So this is after taking positive square root on both sides. What I get is this is this. So if I extract positive square root, this would be modulus of x plus y. will be less than or equal to, yes. So that's what we have. All right. Let's look at the next property. Okay, two more properties we have before. Okay, I would just leave an exercise for you. Exercise here. Show that if absolute of x is less than epsilon, for every epsilon greater than 0, if and only if x is equal to 0. There's no if here. Show that absolute of x is less than epsilon for every epsilon greater than 0, if and only if x is 0. Please prove it. I'll leave with an exercise. Then property number 8, if I'm not wrong, is what we need to prove is maximum of any two numbers x and y is equal to half times absolute of x plus y, of absolute of x minus y rather, sorry, minus x, absolute of x minus y, right, plus x plus y, right. Proof. Let's quickly get the proof done. Okay. Oh, before that, I gotta prove something else. Okay, I can prove that at the last. No problem. Okay. All right. Let's look at this one. Let's draw a shape. I'll prove this and then I'll prove the property which I said. Oh man, this is getting some. Okay. So if I look at this line, if A is here, let me use some different pen. If A is here, this is my A and this is my B, right? Then the midpoint of this would be exactly somewhere here and it would be exactly A plus B by 2, right? And what's the distance of this? First of all, this distance from B to A would be nothing but absolute of A minus B. So let's write that down. We say that it is B minus A, right? Either it is B minus A or it is absolute of, you just subtract, either it is B minus A we say, or it is A minus B and it's negative. One of which of both are equal anyway. So, let's do this. Note that the midpoint of A, and so I've used x and y here. So let's stick to that. X and y is x plus y by 2, right? And the distance of B from A is nothing but absolute of A minus B. Okay, right? If okay, so let me use both the properties here. 8 is maximum of this is this, but anyway, let's look at this one. I can use both the properties here. That would be better. I've just stated maximum. Let me use minimum also. I'll just state a minimum property also here, and we'll prove that both of them one by one. No worries about it. But we can see both the properties. Minimum of x and y, right, is half times its absolute of x minus y negative of um, negative of x. Oh, it's just a mistake. I'm doing some errors. Sorry for inconvenience. Eraser is also not accepting to correct my mistake. Anyway, so this is nothing but x. Let me just check that out. X plus y negative of absolute of x minus y. Okay. So let's look at the proof. Okay, of both, we'll prove both of them. So I want to find what is the minimum of x and y, right? I want to find what's the minimum of x and y, and what is the maximum of x and y. Okay. So suppose my x is this, my y is this, right? And let me just make a correction because I've used a plus b. So this is my midpoint, that is x plus y by 2, right? Irrespective of what is x and y, right? If we move this side, right, to the right half, right, from the midpoint, isn't it? We must get the maximum, isn't it? If we move from the right side of this, whatever the midpoint is from here, if we move to the right side, we would always get the maximum of x and y, isn't it? And if we move to the left hand side, right, from the midpoint, we would get the minimum of x comma y, right? So let's write this, right? If we move to the right half of the distance from the midpoint, from the midpoint we must get maximum of x and y to be equal to x plus y by 2. And what's the distance? The total distance is uh, modulus of x minus y, right? So there, this distance will be exactly half of that. So this would be plus modulus of x minus y by 2, right? Which is nothing but half times x plus y plus modulus of x minus y, right? Similarly, if we move left hand side, let's look at that later, but we'll prove this first before I go to the other way. I would prove this, and then on the similar lines we can prove this. The second one I'll just state later on. Let's prove this first. All right. Okay, we prove this first, and then a similar way I can do the next one. Okay, so if um, uh, b is bigger than a, okay, if b is bigger than, therefore maximum of a and b would be b, right? If b is bigger than a, maximum of b and right, this would be b, right? Therefore what would happen is this implies that this would imply that, and what happens to this? What happens to this? I said x minus y again. Like I'm more used to this a and b, right? Anyway, doesn't really matter. If y is bigger than x, then maximum of xy is y, right? And what happens to the formula? Let's look at this one. And x minus y, since y is bigger than x, this would be negative of x minus y, right? Isn't it? Since y is bigger than x, right, this would be negative of x minus y, which is nothing but y minus x, right? Therefore what happens is x plus y by 2 plus this is nothing but y minus x. This would be x minus x would get cancelled, otherwise this is half times x plus y minus x, right? This and this would get cancelled. This would be 2y over y, which is equal to y, right? Similarly, less than x, then maximum of x and y would be equal to x. And let's look at this one, x minus y rather, right, would be nothing but x minus y. Therefore, x plus y by 2 plus x minus y by 2 would be equal to x plus y plus x minus y by 2. This and this would get cancelled, and what will be left is x, right? Isn't it? So both ways we get same number. Okay. Similarly, also note that if we move to the left half from the midpoint, right, left half of the distance rather, let's do that, left half of the distance, left half of the distance. Okay, left half of the distance of the distance from the midpoint, we get minimum of a comma b, right, isn't it? So if I go to the figure, I'm here, right, isn't it? If I move to the left half, right, then what I'm doing is I'm getting this number, and then I'm subtracting, I'm here, and then I'm subtracting half the distance, right? If I want to go here, right, I am adding half the distance, and from here if I want to go here, I'm subtracting half the distance, right? So minimum of this would be rather x plus y. What am I doing? Minimum of x y, right, would be the midpoint, x plus y by 2, negative of a minus b. That's not a minus b. This is a mistake I do all the time. This is absolute of x minus y by 2, which is nothing but half x plus y negative x minus y. So let's prove this. Okay, by the way, there's a modulus. I just missed. Be careful. This is modulus. Okay, let's prove this. Suppose oh man, again I'm using the same mistake. Okay, anyway, suppose x is less than y. Therefore, minimum of x and y would be equal to x, right? From here, let's do it here. Therefore, what will happen to if x is less than y? Absolute of x minus y would be equal to y is bigger than x. So this is negative of x minus y, which is y minus x. Therefore, half, right, half into x plus y, negative of, this is y minus x, y would get cancelled, this would be plus, therefore this is x. Similarly, if x is bigger than y, right, then minimum of x y would be y, right, and this is same as minimum of x y, right. Therefore, what will happen to x minus y would be x minus y as because x would be bigger than y. Therefore, in this case, what will happen is half times x plus y negative of x minus y would be equal to half times x plus y minus x plus y. X would get cancelled. What we left is y plus y, that is 2y, that is equal to y, which is minimum of xy, right? Isn't it? So that's the proof. Okay, and then the last property we would see is, don't know what's the property number, maybe 8, 9, check out, I don't remember. This is 9th, I believe, that absolute of x minus absolute of y, absolute of absolute x minus absolute of x minus absolute of y is always less than or equal to absolute of x minus y for every x and y in proof. X is always less than or equal to x plus y, right? Isn't it? So we have to be careful here. So let's look at this one. Absolute of x is same as absolute of x minus y plus y, right? This would be less than or equal to absolute of x. Consider this as x, this is y. Then by triangle inequality, this is x minus y plus y. This is by triangle inequality. Therefore, what I get is absolute of x minus absolute of y, if I transfer that side, this would be less than or equal to absolute of x minus y. Similarly, absolute of y would be nothing but y minus x plus x. This would be less than or equal to absolute of y minus x plus absolute of x, right? Which is same as this is equal to absolute of minus of x minus y. Y minus x is nothing but minus of x minus y, right? And this would be plus. But we know that minus absolute of minus x is same as x, because what happens if suppose the number is negative, then what happens? Absolute of minus x, if x is positive, then absolute of minus x is nothing but negative of x. That's x, right? So this is same as x minus y plus x, right? Therefore, if I transfer x that side, this implies that absolute of y minus absolute of x is less than or equal to x minus y, or that is what I get is negative of x minus y, right, would be less than or equal to x minus y. So wherever I had this, let me name this as 1. Okay, this would imply that if I multiply both sides by negative, this will be negative of x minus y would be less than or equal to absolute of x minus absolute of y. Let me name this as 2, right? So what do we get from 1 and 2? From 1 and 2 we get negative of x minus y is less than or equal to absolute of x minus absolute of y, and that is less than or equal to x minus y, right? This implies that x minus y, right, or let me write this down. This implies that by the property number, what? Property number 5, right? Isn't it 5 or whatever it is? Isn't it? Right? This implies that absolute of x minus absolute of y, right, is less than, if I consider this as epsilon, right, and this is my x, right? So mod x is less than epsilon if and only if minus x is less than, minus epsilon is less than x, less than epsilon, right? So if I consider this as x, consider this entire thing as epsilon, this as negative of epsilon, then modulus of x would be less than epsilon, which is x minus y. And that proves the properties which we were dealing with. Thank you. Let's look at more properties next time.